that I'm explaining this article from DeepMind just because it is important. So hybrid computing, this article is the second version of Neural Turing Machine. This paper, which is published in Nature in 2016, this is a positive sample. It's very related to that, very interesting. So DNC is a differentiable neural computer. It stands for that. When trained with supervised learning, we demonstrate that a DNC can successfully answer synthetic questions. I mean, that BABI dataset that I like. It's very simple, like a story, very simple sentences, but we need more complex datasets rather than this simple dataset. And so they can successfully answer synthetic questions designed to emulate reasoning and inference problems in natural language. We show that it can learn tasks such as finding the shortest path between the specific points and inferring missing links in randomly generated graphs. But in this lecture, I only concentrate on the application of this BABI dataset, which is for synthetic questions. So conventional computers use unique addresses to access memory contents. But a DNC uses a differentiable attention mechanism to define a distribution over the end rows or locations of the memory. So we have end rows and M columns. So this is our memory. For example, if you read the article of Carneva machines, they consider this memory as a latent variable, and they did Bayesian analysis over that. But so that these distributions, which we call weightings, represent the degree to which each location is involved in the read or write operation. And the important thing is this, that I have shown it in several papers, that it's just a linear combination of those memory rows. And when we read something, sometimes we want to write something. And these weights are calculated. I will show you in one of the slides how it is calculated. And then we erase here so that we can write here. This is a write vector. And so M times this one plus this one. So this is how your memory is updated, this latent variable in that Carneva machine that they use Bayesian analysis. Here we just update it very simply, just with this simple formula. And the heads use three distinct forms of differentiable attention. The first is content lookup, in which a key vector, and we will see that our controller generates a key. So this is a controller here, like an LSTM something. It creates a hidden variable, and if you use that hidden variable, then you will see it will generate some vectors. That one of them is, for example, the memory is used for memory allocation. It's a very long vector. And after reading, for example, after what we have read, it is coming inside this recurrent neural network, let's say, along with the input. So it's not just the input, it's also something that we have read. And so this is just a recurrent neural network. And recurrent neural networks and hierarchical neural networks are like feed-forward neural networks. But recurrence also happens in the brain. And I will explain in another lecture, a recurrence of recurrence. It means if you want to model brains, we have several recurrent neural networks that they are interconnected with each other, which is more intuitive. For example, this area is doing some cortical, is prefrontal cortex. This is, for example, this could be, for example, hippocampus, or this could be something like amygdala for emotions. So all of these are working as a feedback with each other. So let's get back to that article for DeepMind. And a second attention mechanism records transition between consecutive written locations. So this L of I and J, for example, we understand that if I is used, then the next one is J. So we can record the temporal dynamics of that, of what is written. And we are working with this BABI dataset, which is very simple, like where is the football, and after a long story, we answer some questions. So think about this controller like anything that you like. You can even use LSTM or GRU or any kind of recurrent, or even I can say you can use reservoir computing and fix some, just use a random weights for internal weights, and then calculate and predict the output weights. That is another way. So this is your controller. What is important, it generates you use this hidden value for something. You use that hidden value to generate, first of all, this right vector that I told you, this right vector v of t, and also Kc, which is a long vector. Some of them are for K, which is right key. Some of them are right strength. This is key. This is read strength, write strength, gate access, and many other things like that are written here. So using that hidden state, we understand everything that we need to work with the memory, such as memory allocation and those things. We can do everything with that. So it's like using that, it's just a combination of your history. But we don't use this explicitly. And what is important is this output. It gives you the output as well using concatenation of some R reads and also your write vector. And your read is calculated like this. And you know how this M is updated like this. So we have interface parameter, as I said, this long vector. And here we are calculating the read, we define the read vectors as well. So this is the write, W is write, WR is read. These are read weightings, do not mix them with the write vector. And this dot is just element-wise multiplication, because finally we have a matrix. So these should be element-wise to make sense. And here, this is something that you have seen in several papers. It's like a soft attention. For example, you have a key that is from your question. The controller generates key, and from key, we compare this key to several rows of your memory to see which one is more relevant. Because when somebody says something in our brain just checks which memories are related to what that person is talking about. Because these come to your working memory of your brain, and your brain finally answers something. Very beautiful paradigm, very powerful, because you can explain many things, many connections inside your brain. So we also have a memory retention vector, psi. This is memory retention vector. By using that, we can calculate your usage vector, how much it is used, how much each location, because psi here represents how much each location will not be freed by the free gates. And here, the allocation weighting, which is used to provide new locations, can be calculated like this. So if all usages are 1, then allocations is 0. So if this usage is 1, then this term becomes 0, so there is no allocation. And here we know how memory is updated. We know it's like soft attention. Key is finds the relevant memories. Well, you can see it as a distribution. For example, which row is more relevant. And now that you know this write content, which row is related to that, you can just substitute and calculate this WTW that we needed for updating our memory. And G is just G allocation. And we have also G of write. But G of allocation is the allocation gate governing the interpolation. And this GTW is the write gate. This is the write gate. If write gate is 0, then nothing is written, regardless of other write parameters. It can therefore be used to protect the memory from unnecessary modifications. You know, in our brain, when a neuroscientist talks, he usually talks about just neurons. But there is other cells inside your brain which are asteroids. They keep and clean your neurons. They protect it from damage. For example, if a damage happens to your brain, it protects them. It also regulates them. It calculates the amount of calcium that you need. So it's also used for regulation. And also, it is the roots of that is related to your DNA. And DNA is very important. I don't think it is developed by just evolution, because the probability is very low if it is just by evolution. It should be something mysterious out there. Temporary memory linkage is another important thing that I explain. For example, if we want to know if this is L matrix, if I want to see if I selected, what is the probability that J is the next one. If it is 1, then J is after I. And from L, we calculate this forward weighting and this backward weighting. And this is how we use this forward weighting and backward weighting to update our read vector that we needed. So comparing with neural Turing machine, the neural Turing machine was the predecessor to the DNC described. It uses similar architecture with read-write access, but differed from in the access mechanism. In the neural Turing machine, content-based was combined with location-based, allowed the networks to iterate through memory locations in order of their indices. This allowed the network to store and retrieve temporal sequences in contiguous blocks of memory. However, there were several drawbacks. First, the neural Turing machine has no mechanism to ensure that blocks of allocated memory do not overlap and interfere. a basic problem of computer memory management. Interference is not an issue for the dynamic memory allocation used by DNC, which provides single free locations at a time, irrespective of index, and therefore does not require contiguous blocks. Second, neural Turing machine has no way of freeing locations that have already been written to, and hence no way of reusing the memory when processing long sequences. This problem is addressed in DNC by the free gates used for deallocation. Third, sequential information is preserved only as long as the NTM continues to iterate through consecutive locations. As soon as the write head jumps to a different part of the memory, the order of writes before and after jump cannot be recovered by the read head. The temporal link matrix used by DNC does not suffer from this problem because it tracks the order in which writes were made. And this is the BABI dataset that I explained it. It's just a set of 20 synthetic question answering tasks that are designed to test different aspects of logical reasoning. Because the BABI data are programmatically generated in the code, and the code is publicly available, multiple versions of data can be used. For our experiments, we use the English 10K subset of the data, and you can download it from that website. For each of the 20 tasks, the data comes partitioned into training set when 10,000, so we have 20 tasks. Data comes and we have 10K questions for training. And test set is 10K questions for test set. So the BABI tasks are designed around stories that may contain more than one question. We treated each story as separate sequence and presented to the network in the form of word vectors. After removing all numbers, splitting, it depends on how you put the input. Sometimes you just give sentences, but sometimes you give it word by word. And it will result totally different solutions. Because if you encode sentence by sentence, then you are missing lots of things. It's very conservative. Like a sentence, if you just embed a sentence as just the average of a set of tokens, you see you miss a lot of semantic knowledge and many things. So the sentences were separated by full stop characters and all questions were delimited by a question mark, followed by as many dash characters. So the answer required grouped into milk, apple. The network was trained to minimize cross entropy of the softmax outputs with respect to target words. The output of the controller that I'm talking about, because it has some input. When you read something, it gets something inside it, like a recurrent neural network. And this is memory, that the hidden state is used for updating our memory and looking at the memory. It generates some read, and from read you say some output, but you compare it using cross entropy to the target output and see if the error is small. Then you could do a good reasoning using this very simple BABI dataset. I think in future they should create more advanced and complex dataset because BABI is very simple for reasoning. So using word tokens led to much longer sequences than previous work on BABI. That neural Turing machine, for which sentence embeddings were used as input. The distinction is notable in that it places greater stress on the long-range memory capacity of the models. And in that, the word-level approach is easier to generalize to natural language, which has far greater variability in sentence length and structure than the BABI data.